Hi everyone, I am Xinhu Li from USC. Today I'm going to talk about how we can let the robot learn to show surpassing performance when the demonstrators are facing constraints. This is joint work with Ayush Jain, Zhaojing Yigit Korkmaz, and Erdem Bıyık. Let's start with a problem. In many real-world scenarios, human experts are constrained by their control interfaces or safety requirements, while robots don't. Here is a simple example. On the left, we have a human controlling the robot with a joystick. Because of the interface, the expert can only issue one command at a time. For example, moving forward, then left, then down. So the motion is sequential and relatively slow. Now we replace the joystick with a robot policy. The robot is not limited by the interface. It can execute these movements simultaneously in a single step. As a result, the robot can perform the same task more efficiently than human. This raises the key question. Can a robot learn a policy that surpasses the expert by going beyond the constraints? This problem introduces three key challenges. First, we must decouple the reward from expert actions, since those actions are constrained. Second, during exploration, the agent needs to know which state have reliable reward estimates. Third, for a state never seen in the demonstrations, we still need a generalizable reward signal. To tackle these challenges, we propose LFCD grip, short for Goal Proximity Reward Interpolation. First of all, we learn a state-based proximity function from the expert trajectories. Specifically, we assign each state a temporal distance to the goal, denoted as pow in the figure. Then we define the goal proximity distance as f proxy equals delta to the power of pow, so that the states closer to the goal receive higher proximity value. This gives us a progress signal over states without relying on expert actions. During online rollout, we may encounter unseen states which don't have reliable proximity value. So we interpolate the pow value between two high confidence states, shown here as row start and row end. For any intermediate state, we assign its pow value by linear interpolation along time. This propagates the progress signal to unseen states, enabling generalization beyond the demonstrations. In the end, we train the policy with reinforcement learning, where the reward equals to the proximity difference between two consecutive states. Let's look at a simple but illustrative example in mini-grid. The expert is constrained to move only in four directions, thus the expert trajectory is a blue path. However, the agent is allowed to move diagonally. As shown here, only our method discovers the shortest diagonal path, while all baselines follow the longer expert trajectory. This demonstrates that our method can go beyond the demonstration distribution. We evaluate across multiple tasks, including maze-2D and robot manipulation. The key metric is trajectory length, which reflects efficiency. Across all environments, especially in the constrained expert setting, our method consistently achieves shorter trajectories than all baselines. This shows that LFCD grip effectively leverages the agent's larger action space. Finally, we validate on a real robot, the WidowX arm. The expert is restricted to only move along one X at a time. As a result, demonstrations and BC are slow and segmented. Our method learns a much more efficient policy, completing the task in 12 seconds, compared to 100 seconds for behavior cloning. To summarize, expert demonstrations are often constrained in practice. Thus, instead of imitating actions, we should learn progress-based rewards and discover more efficient behaviors. Thank you for listening.